Good morning, everyone. As you can hear, we're recording this session. Thank you for joining us today. I'm Jonah McLeod, and welcome to the Andes Technology webinar series. Before we get started, I just want to set up a few housekeeping items. The session's being recorded, as we said. There's a Q&A session at the bottom of your screen. If you want to ask a question, please enter the question there. We have a staff on hand. If they can answer the question, they will immediately answer it in text. Otherwise, we'll queue the questions and have Dr. Tran answer them at the end of this presentation. Let me start off by introducing our speaker, Dr. Thang Tran, who developed the innovative RISC-V vector extensions for Andes in a mere 9 months. Very successful design, had 2 design wins almost immediately. So Dr. Tran is no stranger to CPU design, having designed CPUs at AMD, Intel, NXP, and among others, and ARM, among others. So without further ado, I will turn over the session to Dr. Tran and let him begin his talk.
Hello, everyone. I'm Thang Tran. I'm the hardware designer. I have been designing microprocessors for over 35 years. So the webinar is biased toward hardware, but I will try to make it as simple as possible. Okay. All right. So let me start with the Andes technology, introducing Andes technology. So Andes Technologies is a 16 years old pure play CPU IP public company. We are RISC-V founding and premier member. We are very active in RISC-V International and also a major open source contributor and maintainer. Among the quick facts to update, we have a record of 2 billion annual SoC shipments that contain in its CPU IPs into 2020 and at an annual growth rate of 33%. Since inception, the cumulative shipments surpassed 7 billion. Andes Technology headquarters in Hsinchu, Taiwan. We are the first company to commercialize the RISC-V vector processor, including many configurations. And so we are obligated to tell you about the basics of vector processor, the ISA, and some sample codes to show the performance comparison. Andes Technology, the vector processor, won a few awards that you listed here from China Electronic News, from the Aspen Call in 2020 and the Hsinchu Science Park Innovation Award. So we also have a wide range of applications, from embedded MCU to data center with advanced technology on many products, and the chip, the SoC have 1 to 1,000 core, from 40 nanometer to 5 nanometer, and so many adoption in AI. So today, the webinar is the first of the 4-part series, and today we basically have an Andes overview, and then the vector technology background, the concept of SIMD and vector processor. So this webinar requires no prior knowledge or experience with vector processor. So we're going through some vector processor basics. So there are a lot of terminology that for vector processor. So the highlighted here are important. So we have the XIF, which is the integer reservoir. VLEN is for vector reservoir. And so the vector processor, it basically operate on many elements, and with the element width is programmable from 8-bit to 64-bit. And then so the XLEN is the scalar result length in bits. And so in this case, we use a 64-bit RISC-V processor. The VLEN is the vector result length width at 128 to 512 bit. So we designed the first vector processor with the 512 bits. So throughout the presentation, you would hear more about the 512-bit vector result length. And then there is the ELMO with the result grouping multiple. It can be grouping from 1/8 to 8 times the VLEN. So basically, you can group a 512-bit, but you can group 8 of them together into a single vector raster, which is 4K, so 4096 bits. And then there's the maximum vector length, and there's also the application vector length. So let me clarify the terminology that we are using. The first one is configurable. So these are the parameters that can be fixed at build time. For example, the cache size. So if you select the cache size of 32 KB, then that will be a fix on cache size in the design. Extensible, basically these are the added instruction to the ISA, including custom instruction that can be added by a customer, or standard extension. And the standard extension is the reserved code for ISA. For example, you have floating point, DSP, vector processor. Then programmable are the parameters that can be dynamically changed in the program. For example, the element width is the programmable parameter. So RISC-V and RISC-V extension background is an open architecture started by UC Berkeley. So the RISC-V itself is the latest ISA that make a lot of noises in the microprocessor world. It started from UC Berkeley, and the foundation is formed in 2015 with more than 700 members. Andy is one of the first adoptee of the RISC-V. I have designed x86 ARM microprocessor, so I have much appreciation for the RISC-V simplicity. The operand are in fixed location, no status bit, no predication, no lost or double, or lost or multiple. So the instruction set is pretty simple to design. The RISC-V ISA set aside some of the opcode for custom instruction as well as for standard extension. One of the most excited extension is the vector, because it's opened the door to many AI and ML application. As with all standard extension, the vector ISA is defined in a work group with contribution from many experts. The instruction set consists of a scalable vector raster, a data size, and there are over 300 vector instruction, including floating point, fixed floating point, and permutation and mask. So Andy started to work on vector processor since the version 0.7, and at this time we are at version 1.0, and so the version 1.0 RC1 will publish in June 2021, basically last month. And so it's fairly stable at this point. And the version 1.0 is target for public ratification basically by the end of this month. And hopefully the ratification will be done by the end of the year. So we would have a very stable design by then. So let's go to the background of vector technology. First, we start with the Flynn classification. And so you have a instruction stream and a data stream. And so the SISD is basically microprocessor, and the SIMD is the DSP graphic and vector. And SIMD is the most interesting one. It is the basics for which is started with the MMX, SSEs, AVX, Altivac, and Neon. And SIMD is the basic for vector processor. And the difference between a SIMD processor and a vector processor is the programmable vector length. So why SIMD? So when you look at the 32-bit microprocessor, you have one 32-bit element per instruction. With a 5 and 12-bit SIMD processor, you can operate up to 16 32-bit element or 32 16-bit or 64 8-bit element per instruction. And if the SIMD processor clock frequency is at 1 gigahertz, then the performance is basically 64 gigaops. So you increase the SIMD size to get the higher performance. And SIMD is the basic for vector processor and operation per instruction, where the element basically operate independent from each other. So if you have 64 elements, and these 64 elements are actually independent operations, so you have 64 operation of 8-bit, and they are basically independent from each other. And so now if we look at the time and space duality, so we can further define an array processor. Basically, the instruction and data operate at the same time. So this is more like a multi-thread, a multi-core. So when you have the array processor, say you have 4 processing elements, then the processing element execute instruction in parallel. So you have basically the same operation happen at the same time. So you can have 4 low operations that happen at the same time. But if you look at in the same space or in the same processing element, they have different op in the same space. That's different than the vector processor. The vector processor actually look more like a pipeline of a microprocessor, where the load, the add, the mode, and store are in pipeline state. And so, in a way, you can compare to the fetch, decode, execute, and write back that we, pipeline the instruction. So the difference is that you had the same op in the same space. So you have functional unit within a vector processor. So you can have the LSU, the ALU, and the multiply unit. And so basically, you had the same op that in the LSU, or the same add in the ALU. And so basically the same op in the same space. But if you look at across in the time dimension, you have 4 different operations happen at the same time. So the distinguish here between the SIMD and the vector processor is that the low 0, low 1, low 2, and low 3 actually is one single instruction that break up into 4 operations. So it's not 4 different instructions. It's a single instruction that break up into 4. or a single add instruction that break up into 4 parts. The difference for the vector processor is that when you break up the load operation, when the load loading the first part of data, that part of data is now can be forwarded to the add and to the mult and to the store. And so the load does not have to, like in comparison to a RAID processor, you have to load all the data in before you go to the add. In this case, you can load partial data and immediately forward the partial data to the next operation. And that's also the distinguished feature between the vector processor and the SIMD processor. Okay, so let's look at some history of SIMD. So Intel is probably a great example. You can have MMX that started in 1997 that have 57 new integer instruction and 64-bit registers. And so again, the 64-bit register is programmable at an element of 8-bit or 4 element of 16 or 2 element of 32-bit or 1 element of 64-bit. But what happened is we use the floating point register file. And so the floating point and MMX code cannot be mixed. You only do one or the other, but not both at the same time. The number of elements or the programmable or the element width is defined in the opcode, right? So it had to be defined in the opcode. And we only have the consecutive memory load store is allowed. And so it have all the basic function of ALU, mult, mark, compare, pack, and unpack. Then in 2019, now the term SSE that have 70 new instruction, and this time the single precision floating point is added. And so at this time you only have 2 elements of 32-bit. So that's the only feature. And then SSE2 added 144 new instructions for floating point. And now it go up to, the important thing here is go up to 128, from 64-bit to 128-bit register. And then add more instruction, and then eventually the AVX start with 256-bit. And then you had the AVX 512, which have 512-bit register. So each register length have a new set of instruction. And so you have many instruction for 512-bit SIMD. So for RISC-V vector processor, the floating point unit and the vector actually two independent register file. Okay, so vector extension is not a standalone processor; it's an extension. So it have to work with a RISC-V CPU. And so if you had a RISC-V CPU, then you have basically an integer register file, a floating point register file, and the vector data register file. And the vector data register file, all of them are 32 register, can have many elements with variable length. And so the total width of the vector length. So in this case, our design, you have 512-bit here. And so then you have this basically is the SIMD, the vector arithmetic instruction. And so it operates on many elements. And so you have many length for execution. And so basically the vector length had to be greater or equal to the SIMD width. And so you can have 512-bit here, but the SIMD can be 256. Or it can also be the 512-bit SIMD also. And then there's a vector load store instruction that basically can load the data with stripe or with index, which we will go through further detail in the second webinar. Okay. Now, so another terminology that you hear about a vector processor is chaining. As I explained before, so we need an independent functional unit, and data chaining can only happen if the instruction operate on multiple SIMD widths. And so at the example we showed earlier, there's a low 0, low 1, low 2, and low 3. So when it load partial data, it immediately passes that data to the add, and then the add passes the partial data to the mult. And so the data is basically chained in each other. And so if the VLEN is always equal to the SIMD width, then this is a SIMD processor and not a vector processor. And so basically you have one instruction per clock cycle. And so vector means that you can have the single instruction take multiple cycles to complete. And so that's the difference between a SIMD and the vector processor. Okay. And so another view of it is basically, as shown earlier, the element can be break. So the SIMD is, so the number of elements that we need to operate on is 16, but the SIMD can only perform 4 elements at a time. And so you would have 4 elements. So the element 0, 1, 2, 3 will operate first, and then 4, 5, 6, and 7 will be operate second. And so the data can be forwarded from one to the next functional unit. And it shows here that we have a LAN, and each one of the LAN have a single element. And so the data is designed to localize the routing within the LAN for timing. So if you look at the picture, this is a LAN, and so all the data is forwarded within the LAN. So the timing path be localized to each LAN, and it is used for timing also to have multiple LANs. Well, another view. So in this example, you had 32 elements, and so there are ELEN. So you bring 8 units to fetch and execute instruction, and so the fetch data fetch 32 elements in 4 clock cycle, and as soon as the first 8 element data is loaded, it will pass over to the mult, and as soon as the mult can finish operation, it passes to the add. And so the view of chaining of 3 vector operation at the same time. So now, if we compare it to the Scalar code or the SIMD code, then what happened if we had an example C code of basically getting loading the X data multiplied with a constant and accumulate into Y. Okay, and so for the processor, for the Scalar or SIMD code, it will have to load the data and do the accumulation and then return to the loop. And so for scalar processor, this loop will have to repeat the 64 times. If we have 64 elements, then this loop will repeat 64 times. If you have a assembly processor that operates on 4 elements at the time, then the loop here may be for 4 elements. So it would be repeated 16 times for SIMD. But in terms of vector, and so we can have, if we had the vector with the that can operate on 64 elements at one time, then you should have a single, so the code is a one-time code. So basically you had a scalar part followed by the vector operation that operate on 64 elements. So basically it's only 6 instructions in comparison to 9 instructions that dynamically operate 64 times for 578 instruction. Okay. So the advantage of vector architecture is that, if you look at the static instruction for the typical spec 92 FP, the scalar versus the vector is 4.5x in terms of the static instruction. So it will take more code. The code density is much better for vector processor, and it's also, even if if both of them have a single loop, then the vector processor still execute at much faster rate. In terms of dynamic instruction, you have almost 24 times the number of dynamic instruction, and the operation is also, because the loop overhead is also less. So it's the most efficient way for data parallel processing. You have high computation throughput, and it's also require a high memory bandwidth, not low latency. The data operation is chaining, and so the data memory is interleaved for multiple bank for higher memory bandwidth. And so it's orthogonal to the microprocessor architecture. And so you can have a scalar or superscalar microprocessor with the vector unit, as the example with the Cray X1, the alpha, and Andes processor, of course. And so you have the parallel processor that from NEC or from Broadcom. Okay, so let's look at the Cray one as an example that have been around for a long time. I guess it's in 1977. And this was a huge processor or system computer at that time. And so the vector raster is actually 8 vector raster, and each one of the vector raster has 64 elements. And so the element width is 64 bits, and you have the VLEN. It is basically 64 times 64 is 4096 bit. This is actually the Andy vector raster file. It basically the same size as the Cray one. So we design, so it was a huge computer system back then, and now you have a tiny NX27V, which had the same vector raster at the Cray one. And then there are scalar raster, and then the address raster, and there's a 64-bit and a 24-bit. And so these two are now replaced with the RISC-V 32 raster of 64-bit, right? And so the memory bank is 11 clock cycle latencies, and so now it is replaced with the level 1 data cache. So depend on the size that you want to use with the level 1 L1 cache. So another terminology that you also hear with vector processor is the strip mining. And at the example earlier that we have the number of element is 64-bit. I mean 64 element. So we can operate on 64 element at one time. But what happens if the application of the application vector LAN require 200 element? Then you would do 3 iterations of 64 element at a time, and so whatever left over is basically the 8 elements. So you can do strip mining. Basically, you do the first 8 element, and then after that 64 element each. And so strip mining, assume it can be done in software, and it will be similar to loop operation for the other 3 iteration. And the VL is basically the for 8 element, you can use a vector mask register. You can use that to basically to say operate only on 8 element instead of the 64 element. So the technical challenge of vector architecture. And so again, we design the first design was for 512-bit, and so that the VLEN is 512-bit, and so it will be used throughout the design. And so when you had the Vectorize file with 512-bit, the complexity of handling the read and write port with multiple LAN are more expensive in the Vectorize in comparison to Scalar and Flynn point. It's just because it's 512-bit, and 512-bit is huge in implementation and hardware, and so you have to limit the number of the read and write port, right? So for the Scalar, since it's only 64-bit, you can have a lot more read and write port. But for the Vectorize, you had to limit the number of read and write port because it become fairly expensive for the VLAN of 512-bit. And so so if you have a number of functional units, in our case, we implement with 8 functional unit, and in addition to the load store unit. So if you include in the load store unit, we implement 9 functional unit, and so 9 functional unit had to share the read and write port. And so considering if you have 3 write port, right, and you have 4 functional unit, want to write back to the Vectorize file at the same time, it means one of them had to be stored. And so if you store, if you had the result and you cannot write back to the Vectorize file, then it means you had to have a 512-bit buffer to keep that data, because you have a write port conflict. And a 520-bit, and it will back pressure to all the previous pipeline state. So if you have so it also creates a timing path to basically to delay writing back to the Vectorize file. And so you have 9 functional units, and you need an additional buffer because of the back pressure. Then 9 times 512-bit buffer is a lot of resource that you had to deal with. right? Another complexity is basically handling out order execution and retimement. And so in the traditional way of handling out order execution and retimement is that you're using rest renaming or reorder buffer. And so if you have 32 entry rest file as defined by the ISAs, now because of renaming, you add another 32. It's a huge resource of vector raster to use for 5 and 12-bit. So the design will become, huge just to handle the 5 and 12-bit data path and 5 and 12-bit raster renaming. So then okay. So based on that, it basically in order to do an out order execution, it will take a huge resource to implement a vector processor. And also there's some other difficulty is it's expensive to implement a precise exception. And if you have interrupt, it may be a long interrupt latency. But luckily in the AI or embedded market, the precise exception is less important. It depends on the case, but precise exception is less important in comparison to the PC or the smartphone market. And in addition, the vector load store are also very expensive, especially when you have the stride or index load store, which we will go into more detail in the second webinar. And so, well, one thing that we did, we designed the vector processor and simplify many of the above issues. We implement a innovative algorithm to efficiently handle the number of read and write port, and we also guarantee that when the functional unit execute instruction, it will have the read and write port that it needed to read or to write back the data. So it means that we never have any stalling because of the conflict, the write and report conflict. On the other hand, we also allow doing out order execution and retimement, but we do not have any rest renaming at all. So the design is actually high performance, yet it's very efficient because we do not use any rest renaming at all in the design. Okay, so this is the last, well, no, it's not yet. Okay, so the application of vector processor, there are several, including scientific computation, engineering computation, multimedia, standard benchmark, and of course, one of the major application is artificial intelligence and machine learning. It can also be used for compression, cryptography, speech, handwriting, operating system, networking, database, and language. Okay, then let me close the first webinar with the overview of the NX27V. And so vector is a co-processor of the RISC-V microprocessor. So we use the AndeStar V5 architecture, which is a 64-bit 5-state pipeline. The microprocessor has many options, including plan prediction, instruction, and data cache, and the multiply, divide, and of course the VPU and FPU. The LSU handle hardware unaligned address and non-block non-blocking access for VPU. VPU including both catch and uncatchable and custom access to the external coprocessor and local memory. So it will go to the external memory through the BAU using AXI, or the streaming port. It allows you to access to the local memory. And so we had this is the custom instruction that allow you to efficiently fetch the data from the local memory. The custom instruction is actually have all the feature of the normal vector load store instruction. And so the vector load store unit actually allow, beside non-blocking, it also allow out order data access to external memory, which is necessary for good performance. And the important feature of the VPU is actually here, the VLEN width of, so currently we have the configuration of 512, 256, and 128-bit. And so, and the bus is also can be configurable from 128 to 512-bit. Okay. So yes, so we are basically done. And one more slide, the vectorize. So you had different image width and the vector length of all different size. And so you can find the latest trend with the Andes. And thank you.